So we are going to determine MD and MF as a function of ME and MP. This is our structure. And with the assumed mechanism, we have equilibrium set. As you can see here, here is MP, and here is MP, and MD, ME, and MF. Actually, we don't know MD and MF and also ME, but we assume this is redundant ME. And now we are going to determine MD and MF as a function of ME and MP. And this is an equilibrium set, okay, in general. And for MD, for determining MD, then we have a geometry set for MD, like this. Okay, we use this geometry set for MD. Here, minus theta. Okay, this angle is minus theta, and here also minus theta, and this angle is 2 theta. 2 theta. It is geometry set, okay, or displacement set. Displacement set, and this distance is L over 2 theta. Then we have equilibrium set for this one is MP at this point, MD corresponding to this, and ME corresponding to this, and the load is P. Okay, the load is P corresponding to this displacement. Then we can easy to write down to develop the equation. The work equation. Can you write down the work equation by yourself? What is internal work? Internal work equal to MP multiplied by minus theta and MD. Okay, MD minus multiplied by 2 theta and ME multiplied by minus theta. External work equal to P multiplied by this one. Okay, so internal work equal to external work. Then you have this equation: minus MP and minus theta, and MD minus multiplied by 2 theta, and ME multiplied by minus theta equal to P. And here is P. Okay. In the previous step, we already determined P, and it is 3 MPL P multiplied by this L of 2 theta here. Okay, then you can solve this equation. Then we have MD. MD is unknown, equal to the 1/4 of MP and half of ME, because we try to determine MD as function of MP and ME. Okay, so similarly for MF here, for MF, the displacement set, okay, or geometry set for MF is like this. Again, we have minus theta, 2 theta, and minus theta. That is displacement set, and we also have equilibrium set, including ME, MF, and here is 0. It is moment, and P, and P equal to this one, we already know. Then could you please write down the work equation for MF? Please take 1 or 2 minutes to write down the equilibrium, the work equation for MF. Okay, so we have external work. External work equal to P multiplied by this distance. This one equal to 1.5 L theta. Divide by 2. Okay, divide by 2. Okay, so because you remember that this length is 1.5 L. Is this right? Then half of that theta. Then it is the distance. Okay, that is external work. External work. And how about internal work? Internal work is ME multiplied by minus theta and MF multiplied by 2 theta. Then we have this equation, okay? This equation. Internal work equal to external work. By solving this equation, we have what? We have what? MF. MF as a function of MP and ME. A function of MP and ME. Now do a moment check. Moment check. M at every section. Okay, M at every section should be smaller than MP. If that condition is satisfied, then our solution is correct solution. Okay, so we have to check, or we have to M at D should be greater than minus MP. M at D should be greater than minus MP. I'm sorry, here, not here. M at D should be greater than minus MP, and it should be smaller than MP. Okay, the range of M at D is minus MP to plus MP. Okay, MP minus MP. So here, this is MD. MD here should be greater than minus MP and smaller than MP. That is the range of MD. And similarly, we have ME. ME also greater than MP, greater than minus MP and smaller than MP. Okay, and also MF equal to this. Okay, this equation, and also MF. This is MF. MF should be in the range of minus MP and plus MP. It is plus MP and minus MP. This range. Then we can solve this equation. So here we only have MP and ME. MP and ME. Then solving the equation, we have ME as a function of MP. Okay, we solve ME as a function of MP by solving 3 equations. Okay, let's see. The first equation, we have ME in the range of minus 5 2 of MP and smaller than 3 divided by 2 of MP. And here, the second equation, same. The third equation, we have ME greater than minus 16 divided by 4 MP, and it should be smaller than minus 1 over 4 MP. So, combining three equations, we have ME in the range of what? In the range of what? Minus MP, okay? Greater than minus MP, and smaller than smallest one. Smaller than smallest one. Greater than the smallest one is MP, okay? Is MP. And it should be smaller than the smallest of 3. It is minus 1 over 4 MP. Then it is range of ME. Okay, range of ME. If ME in this within this range, then our solution is satisfied. Moment condition is satisfied. Okay. If ME is out of this range, then our condition is not satisfied. Moment condition is not satisfied. Okay. So it is range of ME. It is noted that, okay, note, if ME has a range, okay, if ME has a range, ME has redundance, okay, so means if the redundance of the solution, okay, if redundance has a range, then the mechanism is correct, okay, and the solution is correct. Again, if our redundance or some redundant has a range, then the mechanism, the assumption mechanism is correct. It means solution is correct. Okay, remember our redundance is ME and it has range. Okay, it has range. ME is in this range. Then our assumed mechanism is correct. Then our solution is correct. Okay, so remember. And the second is in plastic design. In plastic design, okay, in plastic design, we don't need a unique value of ME. Okay, in plastic design, we don't need a unique value of ME. It is range, it's okay. Okay, in plastic design. So it is a very new concept. Okay, in plastic design. So it means that our solution of ME in this range is correct range, and we can use this range for next step. Okay. So by using this solution of ME, now we can plot. Now we can plot the moment diagram of the given structure. So moment here is MP and here is MP. Then we have MD in range from here to here. ME, ME. We have range. Here's range of ME from here. Okay, 1 over 4 MP, 2 MP. And we have range of MF. Okay, MF. MF is from here to here. So the important thing is that moment at every section is satisfied with moment check condition. That is important. Okay, that is important. So if we let me equal to minus MP, okay, if we let me equal to this one, the lowest one, the lower value, then MD equal to this one, MD equal to this one, okay, this one, and MF equal to this value here, this point. So it means if we let ME equal to minus MP, this maximum value we have, then this continuous line is used. Okay, continuous line is used for moment diagram. But if let ME equal to the upper value, this one, okay, this one, then we have MD equal to M divided by 8, MP divided by 8 here. So very small. And MF equal to MP here. So it means if we use this ME, then we have moment diagram curve is this curve, the dashed line curve. Okay. So we have range of MD and range of MF as a function of the range of ME, and all the section moment at all section is satisfied with moment check. Okay, so our solution is correct. Our solution is correct. Okay, now please move to another example. Previous one is analysis example. And now I'm going to tell you one example on design problems. Design a photo frame. Consider a photo frame as you can see in this picture. Okay, so A, B, C, D, E, F. Here the load is 80 kips and 60 kips at C and D. And the dimension of the structure is here. The beam has a section of 2 MP and the column has a section of MP. And MP is unknown. Dimension is given and the load is given. And MP is unknown. And we have to determine MP. We assume B1 equal to B2 equal to 1. And Kx equal to Ky equal to 1. Okay, I think you understand the meaning of this. If you don't understand, so please back to the previous lecture. Okay, I already mentioned the meaning of this one. So if you don't understand, so please just back to the previous lecture. So determine MP. We assume the steel A36 and web section. Okay, W section. Assume mechanism. We assume mechanism like this. Okay, here is a plastic hinge at here, this point and this point. Then we assume here is theta, and here also theta, and here is 2 theta, and here 3 theta. The deflection here is 220 theta, and the deflection here is 2 theta, 10 theta. So here is we already have equilibrium set and the displacement set. Okay. Then now we can develop the work equation. External work equal to this one plus this one. Okay. This one plus this one. External work. And internal work equal to MP multiplied by here, and this one multiplied by 2MP, 2MP of the beam multiplied by 3 theta, and MP multiplied by theta here, this section. Remember, at this joint, we use some smaller value of MP, okay? So here MP and here 2MP, then we use MP. Then by solving this equation, we have MP equal to 244 kfeet. Okay, so based on this assumption mechanism, we have MP equal to 244 kfeet. That is solution of MP as corresponding to the assumed mechanism. And now we do a moment check. We have equilibrium set. Okay, for moment check. Now we have here's MA and MP here, MD and M minus MP. We already know here and here are MP and 2MP. The unknown is MD and MA. Then we have to check MD and MA. Okay. For MA, we use this mechanism. Okay, we use Sway mechanism for MA. With this mechanism, we can develop the work method. Okay, work equation like this. You can check. Okay, you can check, and then we have MA equal to 0. It's okay. Good. For MD, we use this mechanism. MD, we use this mechanism. Okay, or we use this displacement set. Then we write down the work equation is like this. Then MD equal to this one or equal to this one. It is smaller than 2MP because it is beam. Then it's okay. Okay, it's okay. So MA equal to 0. MA equal to 0 and MD equal to this one, 422. And here's MP equal to 222, and it is 2MD MP equal to 488, and here's MP and here's 0. Then we have moment diagram of the given structure. Okay, of the given structure. This is moment diagram. MA equals 0 and MP here, and 2MP and MD and MP here. Okay, and 0. Then we have moment diagram. And based on this moment diagram, we have member force at beam and in the beam and in the column. Okay, member force in the beam and the column. Based on this diagram, then we can easily to determine the moment force in the member. Okay, you can check moment, the force in each member in the beam and in the column like this. Okay, you can check by yourself. So by on this one, we can continue with next step design.